All right, so we're going to carry on with our discussion about chapter two, which is our first look at derivatives. But before we go any further, I would like to take a step back and revisit some of the earlier sections just to make sure we're getting the hang of it, and also to do some of those knowledge checks that we kind of skipped over before. This is a part of the course where, the more practice we get, the better, hands down. It takes a while to learn how to use these rules, but I mean, once you do get the hang of it, it's fine. But in the early days, it could be a little bit overwhelming with all these new things to remember. So I want to sort of take a step back and revisit some of the things we were doing earlier. For example, why don't we go back and revisit some of the basic rules of differentiation? The constant rule, of course, is it couldn't be any simpler. And just remember that the derivative of a constant is just zero. Okay, so we often ran into this when we were taking the derivatives of polynomials because there's usually a constant term in there. So whatever the constant happens to be, its derivative is zero. Okay, so that's the easy one. I'll just label that here. Then they introduced us to the power rule. Now, this is the one that we use all the time, and variations of it, I should say. So here's the power rule. And that just simply means that if you take an expression like this, x to the n power, then the derivative is nx to the n minus 1. Okay. Now, sometimes, like you have to be careful with it because let's say it's easy to see what to do with x cubed. It's going to be 3x, and the exponent is actually 3 minus 1, which is, of course, 3x squared now. But if you have just plain old x, remember there's an implied 1 exponent here. So therefore, we end up with 1 times x to the 1 minus 1, which is 1 times x to the 0. But 1 is just 1, x to the 0 is 1 as well. So this is 1. All right. And then we went on to, and they give us a few other examples. Constant multiple rule. Now, anytime, no matter what the situation is, if you have a constant involved in your derivative, um, let's say you have, and they're giving it a separate name, the so-called constant multiple rule. Not every book uses the exact same terminology for these. So basically, what's happening is that whenever there's a constant, you can simply factor it out and then apply whatever rules are appropriate. So here you would have c times f prime of x using whatever rule we happen to need. And so you can see how this would extend our ability to do the power rule because if you have something like this, so the 4 stays on the outside, then you have 5x to the 5 minus 1 using the power rule. And that would be our final result. So if you run across, let's say something like this, let's say it's 3x. So you're going to have 3. And again, remember, there's an implied 1 here. Okay. So that leaves us with 3 times 1, which is just 3, x to the 0, which is just 3. Okay. So whenever you're differentiating x or a function of x, or a constant times x, you're going to wind up either with x with 1 or a multiple of 1. Um, and then, of course, even here, just a constant leads us to 0. And then they gave us a few more examples, which we looked at. And then here's where they formally combine these with the power rule. So in other words, in the specific case of the power rule, Then this becomes c times nx to the n minus 1. Of course, this is the result of using the power rule. All right, so if you ended up with, let's say, oh, 3x to the fourth, and you'll end up with 12x cubed, okay? Or, now this will just be 2 for the reasons we just explained, because what you really have here is 1x to the 1 minus 1, which is just 2 times x to the 0, which is just 2. Okay, so you'll recognize this from as soon as you see it. It just becomes 2. Sum and difference, these are very straightforward. And now every time we apply these rules to a polynomial, this is exactly what we're doing because we have all these individual terms. We're taking the derivative of each term individually and then recombining them by either adding them or subtracting them, as the case may be. So you can write this in a more compact way. Some books do this. Um, let's see. So like what I'm saying is you can do this. The book does this sometimes. This time, I guess they chose not to. So you're basically just taking the derivative of each function separately and then either adding or subtracting them, as the case may be. So, like if you have, oh, look, what a mess. So what you're really doing, although you don't have to write it out like this, is you're individually evaluating these derivatives using the rules that we just learned. Let's write it like this. Oh, sorry, that's not right. I've already got 4x, negative 4x squared. This is the 7x. And then what I could have done is just factored out the constant in the beginning. Just make sure you don't lose track of the signs when you do this. It's so easy to do. All right, so what you really have is 3d dx of x to the fifth minus 4d dx x squared plus 7d dx x minus d dx1. And now you're applying the power rule here to each of these terms. And then you're adding and subtracting. So you end up here with 3, 5x to the fourth. Actually, let me not skip a step here. All right, and then we'll have 7. Now here, there's an implied 1 here. I can write it like this, 1x to the 1 minus 1. And now this is just 0. You don't have to mess around with it. It's just 0. So we ultimately end up with 15x to the fourth minus 8x plus 7. Okay, so remember the original function was here. And so our conclusion is that this equals 15x to the fourth minus 8x plus 7. Okay. So anytime you deal with polynomials like this, you'll end up with the same process. All right. And then, of course, don't forget about the trig functions. These, there's it's something you should probably just memorize them. The other day, I did show you a derivation for one of them, but basically, here you're only expected really to just remember them, or at least be able to look them up when you need them. So, in a more advanced class, you might go ahead and go back and revisit these and prove where they came from. But no, here we're just learning the rules. And after a while, you'll have some of them memorized, whether you whether you're trying or not. You'll see them often enough. That's how it works sometimes with things to memorize. If you see it enough, you don't even have to make the effort to memorize it. It's going to stick in your memory no matter what you do. Okay. Now, later on, for some reason, they waited to show us the rest of these. Um, but all right, so let's do this. Just to make sure everything's fine, that we all get what we're doing, let's run through this knowledge check, and then we can come back and revisit the trig derivatives. I guess they decided to save those for another section. So if we have um, minus 5x cubed minus 2 sine x. Now, obviously, we're going to apply the power rule over here on the left, and the right will apply the derivative of the sine. Okay, so let me just neaten that up a bit. And there we are. And so which one is that? Minus 15x squared minus 2 cosine x. Yep, that's it, D. All right. So I think what they mean for us to do here is they mention in the chapter that velocity, but then they have V0, and I'm not sure what they're doing there. Let's just skip over that one. I'm not crazy about physics examples because then you have to get involved with explaining the physics behind it. And so I think we'll jump ahead to 2, 3. And we're going to go back and revisit some more rules that we know where they're starting to get a little bit more intense, like the product rule. Okay. Now, here, unfortunately, you would like to think that, all we would have to do is multiply f prime by g prime of x, but it doesn't quite work out that way. So here's something that you basically have to memorize. Now, and by the way, we did see later on that there's more than one way of expressing these results using the notation for derivatives. Um, I find the book sometimes isn't completely consistent about that, but as long as we're familiar with all the different notations, we should be in pretty good shape. All right. Now, I remember the last time we met, they had a summary chart of derivatives rules, and what they did was they swapped out u for f of x. And this is not unusual to see this notation. And if you see that, it just means you're going to write it like this, where v prime. Sometimes you see u written as u of x, v is sometimes written as g of x. It's the same thing. Okay. So just be careful with it. Also, when you're writing this down on a piece of paper, be aware that if you're not careful, U's and V's start to look very close to each other. So what I try to do here is go out of my way to emphasize the sharp point on the V to make sure you can see which is which. Okay. So you just have to be careful. Now, let's do an example. Um, I'll make up my own. I don't want it to get too messy. No, that's too messy. Let's try this. And then g of x can be, let's say, 4x plus 2. All right, so imagine that you were being asked to solve for, and you say, I know how this works. Before you do anything else, I would think your best bet is to go ahead and solve for f prime of x and g prime of x, and then it's just substitution. So here we're going to use the same rules we've been using. Um, this one will be 2x to the 2 minus 1 plus 3, which means 4x plus 3. G prime of x, even simpler, is 4, 1, x to the 1 minus 1. And this is just 0. You can just write it like that. Just 4. Okay. Now we plug in these expressions into the definition. Okay. Now, it's way up here. So let me copy these again. So, all right. So we should be able to see everything we need. So we're going to have f of x is 2x squared plus 3x. G prime of x, as we just showed, is 4. And then we need the g of x. And then f prime of x, which we just proved up here, is 4x plus 3. Now, the first one is easy to expand. I'm guessing that when you do this in WebAssign, they're going to ask you to do what we're doing here. Now, as far as the second part goes, we might as well use FOIL. I'll put it aside over here. And we'll do a FOIL on it. Okay. F is here. That would be 16x squared. O is 12x. I is 8x. And then last is 6. So we consolidate those like terms. And so what you're seeing here is this. We're going to replace that with, once again, 16x squared plus 20x plus 6. And now we just combine the like terms and write it as a single polynomial. Yeah, hold on. Yeah, I'm so used to writing on a whiteboard. There really isn't a whole lot of room on this document. That is kind of an awkward thing. Now, there's a way that you can split the screen um, to make it easier, but I've got all this other stuff covering it up. So we've got to, here we go. There. So if you use Word at all, this on the view tab, you've got this the split. And what it does is it lets you treat two parts of the screen independently. So what I can do is scroll up here and then I can copy down here and I can see what I'm doing. Okay, so that's going to make things a lot nicer. So what I'm trying to show um, is all of those terms. Let's copy them one more time. 8x squared plus 12x plus 16x squared plus 20x plus 6. Now I combine the like terms, meaning all the ones with the same exponents, and the constants go separately. I have 2x squares here, 24x squared. There's two x's here plus 32x plus 6. And if you notice too, the exponents are listed in descending order. Now, I'm pretty sure that if you enter this into WebAssign, they're going to insist that you do it this way, and they may actually mark you wrong if you get it out of order. So be very careful with that. Okay. So this is the final result right here. All right. Now we can do the same thing with the quotient rule. We just remind you, oh, on the Mac, you have to hit the remove button. On the PC, you can just double click that. Okay. So let's go back to the slides and look at the quotient rule. Oh, come on. And it's a little bit messier, but it's awfully, awfully important. See, they did one very similar to ours, didn't they? Um, yes, they did. Oh, you know what? Before we do the quotient rule, let's try this one just to get some practice with the trig functions. All right, so here you've got, oh, sorry, there's no two there. 3x squared times sine x. Okay, so this is your f of x. So yeah, these are very straightforward because f prime of x would be 2. Actually, the way we've been doing it, the 3 is usually kept on the outside, the constant 3. So we'll do it like that. 3, 2x to the 2 minus 1, or 6x. And then g prime of x. If you remember, I did say that eventually you'll have these rules memorized. Okay. So now we apply the rule, the product rule, that is. And we just plug everything in. So f of x was 3x squared cosine x, and g of x was sine of x. F prime of x, as you can see there, is listed as 6x. And, just by convention, we're going to rewrite it slightly. Now, whenever trig functions get involved, what sometimes happens is there could be an identity in here that you might not even recognize. If there is, you might be able to simplify this even further, but that's not the case here, okay? But we do want to keep our eyes open for those. You never know what, oh, I see what they did. This is what we got. Then they chose to write it like this. That's not absolutely necessary. All right, so now we are ready for the quotient rule. There we go. And of course, it's understood that in an expression like this, we can't allow g of x to be 0. Or, remember, there's another way to write this. Just in case you run across this in the book, this is what they are referring to. It's the same thing. Sometimes it's just more convenient to write it with U's and V's. Plus, probably over the centuries, different mathematicians chose different forms of notation and they just stuck. Okay. It's not like one person invented all of this and decided to use this consistent notation. It just didn't work out that way. Okay, here we go. They've got 5x minus 2. It's like, imagine how convenient that would be if we kept stuck with the Latin and every one of the European countries are still speaking Latin. Well, that would have been nice, but it didn't happen. Okay. 5x minus 2 over x squared plus 1. So we'll think of this as our f of x. So applying our rules that we know, we can use here remember they called it the constant multiple rule or whatever when you're doing the power rule with a constant. Um, and then we just have 0 here. So this is 5x to the 0, which is just 5. Okay. G of x. So we're applying the power rule to both of these. So this is technically 2x to the 1. We'll just call it 2x, and then we have 0, so we end up with 2x. So now we just plug everything in. Let me copy the rule one more time so we can see what we're doing. And again, it may look like a mess, but you'll have this memorized very soon. You might not think so, but you will after using it enough. All right, so we need um, all right, we have x squared plus 1. F prime of x is 5. F of x was f5x minus 2. And g prime of x is 2x. And of course, g of x is, again, x squared plus 1, so that will get squared. So now we can simplify the numerator. Here we've got to watch it because there's a negative. So the first one is negative 10x squared plus 4x. And then we, of course, consolidate the like terms. And this should be good enough. Unless there's something in the denominator that evenly factors into the numerator, which is not the case here. we can just leave it like this. Sometimes, you can get very clever and find ways to simplify, but this one is fine. And I don't know what that's for. Anyway, here's the rest of the trig functions, and so we'll just make a note of these. We'll copy them. Something like this, they're bound, I'm sure there are tables. In fact, I probably, in the beginning of the semester, I just remember we have all these wonderful tables in Brightspace. I'm pretty sure that I would have included one of these. Hold on. Oh, here we are. I just want to confirm that. If not, I'll make that list up and put it in there, but I think it is in there. Oops. Got so many schools here. Yeah, see, they started doing this recently. I don't know what that even means. What is the Microsoft Authenticator? I have no idea. So I'll sign in another way, the old-fashioned way with a text. So, I'm still a good 10 years behind the technology, but I'm getting there. All right, here we go. Just to make sure. So this way, when you're working on these problems, you don't have to search around and look for all these formulas. Huh. Well, this one says basic rules of integration. Oh, sorry, that's the wrong one. That's down the road. Don't worry. Ooh, don't worry. Differentiation. Um, I think that's chapter 4. Basically, integration is the reverse of differentiation. Here we go. So if it's not already in here, oh, you know what I must have done? I must have done this. Oh, here it is. It is all here. That's good. That's good. I clearly didn't have time to type it up properly, so this is what we have. So, it's kind of convenient. I think I covered them all. Just remember that it's here if you need it. Okay. Yeah, I like this. All right, there it is. So anyway, let's get back to this. So these are our trig derivatives. The rest of them, that is. Now, these trig derivatives, by the way, the reason why they showed us the first two in the beginning and then saved the rest for later is because every one of these that you're seeing here can be derived from the first two. They're not really new information. Okay, I just want to mention that. So, secant squared x, and nobody expects you to memorize these. There's certain ones you should memorize, like the sine and the cosine. These, eh, you can get away with looking them up in a table. Cotangent, negative cosecant. Oops. Oops, cosecant squared. And then finally, the last one is cosecant, negative cosecant, x cotangent. Now, one thing you should also memorize, don't forget the basic relationships between these this will help you out tremendously as you go along. If you remember, for example, that the tangent of x is the ratio of the sine of the cosine, the cotangent of x is the inverse of that. The secant is the inverse of the cosine, and the cosecant is the inverse of the sine. It'll help you tremendously if you have these memorized. Okay. And you'll see as we go along, especially, the further you get into calculus, these will pop up all the time. And then there's some other identities that as we go along, I'll show them to you and recommend that you memorize those as well. Okay. Anyway, what came after this? Higher order derivatives, you can reapply those rules as many times as necessary. Just be aware of all these different notations. Um, it can get confusing in some cases. Some of them are very straightforward. But I think I mentioned this the other day. In practice, it's unusual to need derivatives that are higher than second order. Third, maybe once in a while, is very unusual. Normally, the first and the second are what we need. And so you can write the first derivative. We've been calling it up to this point the derivative, which is correct. But to distinguish it from the others, we can call it the first. We can call this one the second. And that every time you have a new derivative, you just add some more primes. Now, at this point, some books do something a little different. Instead of going on to four, you sometimes see just four or the Greek, the Roman numerals for some in some books. Otherwise, after a while, it's hard to, if you just have a bunch of primes there, it's easy to not see the difference between, let's say, five and six or whatever. And then the corresponding ones, you also have the dy dx. Now, the dy dx's are a little bit confusing because of the way we place the exponents. So the second derivative is actually the derivative of the first derivative. So what you're doing is this. So then the way they represent that is d squared y over dx squared. And then after that, they're all the same. In other words, the third derivative is the derivative of the second derivative, of course. And then it goes on from there. So that notation potentially could be very confusing, but when you have primes, it's easy. It's easy to see what's going on. So literally all you're doing is reapplying the same rules as many times as needed. And we did this one already. They're showing us the position, the velocity, which is the first derivative, and then the second derivative is the acceleration function. Okay, now this is one we did skip over, I believe. So let's try this. X to the fifth minus 3, x cubed plus 3. So appears to be a pretty straightforward product rule. There's no trickery involved. Sometimes they do. Sometimes these expressions can get tricky. So using the power rule, we have 5x to the fourth over here. G prime of x is 3x squared. So Actually, you know what I just realized? This is where we have to be a little careful. If I'm going to call this one f of x and g of x, I probably should change the name over here to h of x. And then that way I can now call this whole thing h prime of x. So let's go through the product rule. And now we just substitute. All right, what do we have? X to the fifth minus 3, 3x squared. Um, X cubed plus 3. And finally, we have 5x to the fourth. So we multiply them out. 3x to the seventh minus 9x squared. 5x to the seventh, 15x to the fourth. And don't forget, by the way, if you're getting a little rusty, this is the product rule for exponentials. So the reason why x to the fifth times 3x to the squared is 3x to the seventh is because I've simply added the 5 and the 2. You can do this as long as you have the same base. Okay. All right. So let's combine the like terms. As always, that's going to be 8x to the seventh. We've got a 15x to the fourth and minus 9x squared. Notice again, that I'm writing them in descending order of the exponent. All right. So what do they have here? It would be D right there. All right. And then, of course, here's a quotient rule. I don't think we did this one. Let's try it now. Oh, and just to be in the safe side, I'll tell you, let me call it h of x just to avoid any confusion. Um, X plus 4, it makes no difference what letter we use. What is it again? X plus 4 and x squared plus 9. So this becomes our f of x. This becomes our g of x. So f prime of x is just 1 because we have x. Remember, when you differentiate x, it becomes 1. And then g prime of x, applying the power rule and the constant rule, gives us 2x. So we have, and now we make the substitutions. And it'll take a while to memorize this one, but you'll get it. So f of x was x plus 4. G prime of x is 2x. And again, g of x is x squared plus 9. All right, let's see. So we can have to, now this one, x squared plus 9, we don't have to do anything with that. Here we're subtracting, so be very careful. We're going to have minus 2x squared minus 8x. And once again, we combine the like terms. All right. So unless they decided to, oh, they changed it a little. I see that. That's weird. Did you notice? Look over here. Oh, but then there's a negative on the outside. That's why this is why we do it that way to avoid any confusion. If you notice, this one could be rewritten. So it is B, but normally the convention is to do it like this. I don't know why they would do that, but that's what they did. Maybe they're trying to trick us, but the answer is B. So if WebAssign tries to trick you like that, just be aware that, you might need to simply rearrange it algebraically. All right. I hope they don't do that. There's no, in my opinion, there's no room for trickery in math. But all right, now two fours, we just started to go over last night was the chain rule. And the chain rule is kind of a complicated rule. Um, we start with the so-called general power rule. Now, what separates this from the others is that what's going on inside the brackets, that U term is a function of X. It's not just X, it's not X to raise to some power, it's a function, which could be anything. And so that makes things a lot more complicated. So, and again, you notice how the notation is starting to get a little different again. We're using U's in here. So we have to be comfortable with all these different, notations that will spring up. So we'll start, this is the general power rule. The chain rule is related to it. So if you have U of X to the n power, you're going to have n U to the X, n minus 1. But then we also need either U, they're going to either write it as U prime or du dx. So you can write this as du dx. They all mean the same thing. Ah, okay. So once again, there's many different ways of expressing this. So let's see what example they came up with for us. This is a good one. F of x is 3x minus 2x squared cubed. So this is the challenging part. We have to make sure we are sure what is u of x and what is n. So here n is the 3, and this is what we mean by u of x. Okay. And we now need to know du dx. So we have 3, 1, x to the 1 minus 1, minus 2, 2x to the 2 minus 1. This is just the u of x, by the way. Okay, you notice how we're only applying this to what's inside the parentheses. We're applying the power rule that we learned in earlier chapters. So what you actually end up here is this. So therefore we have 3. So remember, n is 3 in this case. U of x is that 3x minus 2x squared. And then we have du dx, which is that 3 minus 4x. Okay, so we have n, u of x. This is our n minus 1. Now we can go ahead and simplify it by multiplying this by these two terms. And that should do it. Now they didn't even bother with that. They left it like this, which is fine. In other words, they left it like this. Okay. Um, and then the chain rule can be applied to the trig functions. Now, the chain rule is formally written like this. As so often the case now, dy dx can be decomposed into dy du and du dx. This is often the easiest way to do it. Or you can say, well, what are we actually doing here? We're taking the derivative of a composite function. Okay, so they're going to give us quite a few examples of this. And like here's some right here. Like, for example, I think we did this one right. Let's try it again because it's a very straightforward one. So what's happening here is that we can approach this in a couple of different ways. Um, you could think of this as and then that means that f of g of x is x plus 2 cubed because this is g of x right here. And then you can apply what you're seeing here. And the reason for this is that if g of x is x plus 2, g prime of x is 1, and f of x is x cubed, then f prime of x is 3x squared. So you're basically combining all these terms. Now, in the book, what they'll often have you do is this, okay? And you might find this a little bit more straightforward. Think of this as u, then du dx is 1. Um, and so if you write y like this, then dy du is 3u squared. And so remember earlier on we said that one way to express the chain rule is right here. And so what you've actually got here then is dy du, du dx is 1, but u itself is x plus 2, and that's your answer. Okay. Yeah, there's so much writing in here. I want to make sure we didn't lose track of it all. So B should be um, Oh, something's not right. Oh, I think I didn't. Did I copy that right? No, you know why? Because I didn't copy it right. Or wait a minute. What's happening here? No, they're not copying it right. Look at that. It is x plus 2 cubed. But then all of a sudden, this one is x squared plus 1 cubed. So, all right, that's pretty ridiculous, but let's try that one too. I thought I did something terribly wrong. No, they changed the example. Let's try this. Y is x squared plus 1 cubed. So if I let this be u, du dx is 2x. If y is u cubed, dy du is 3u squared. So therefore, 3u squared, 2x, and this is our final result. You can leave it like that, or you can consolidate it. So you can see that once you get some practice with this, I think you'll find that with the chain rule at least, this du dx stuff right here, this might be the way to go. Because it's easier, I think, to identify what is u and what is y, and then you differentiate them, and then you just plug everything in and you're all set. Okay. And then that leads us up to the general. The general power rule comes from the chain rule. It's a specific example. All right. Anyway, then we have the trig functions. And remember, we did this once before. Instead of the derivative sine of x, we have the sine of u, which is a function of x. And so based on the chain rule, this complicates everything a little bit because now the result is not just cosine u, but then we need this derivative of u as well. Okay. So for example, now remember, u itself is a function of x. So the derivative, um, and you could also replace this with u prime of x or just u prime, depending on your preference. So if you're looking, for example, at, we're going to let u be 3x squared, du dx is 3x, sorry, 6x, based on the product rule. I'm sorry, the power rule. So therefore we have, okay, so think of this, and remember, y would then be sine x and dy du, sine u, I mean. So we have, this is our cosine u, and then du dx was the 6x. So now we replace the u with the 3x squared, and we're all set. Okay. And again, you'll get better at this with practice. It seems like a lot right now. And then there's a chart where they suddenly introduced all those u's and v's on us. Okay. And then we also have this final knowledge check. This is the last one that we skipped over. I thought it might be a good idea to give you a minute to, or some time to practice with it, but we may as well get it done now. Um, let's see. f of x to the 7. Now, it is a very straightforward product rule, except for one tricky part. Um, so here's what we'll do. I'm going to write this as h. I just like it this way. F prime of x, we just simply use the power rule. Now, g prime of x, though, requires the chain rule. That's why they're doing this. So let's take a look at this one. So let's let u be 5 plus 8x. And y, of course, becomes u cubed. And dy du would therefore be, based on the power rule, three u squared. So remember how this works. 3u squared times 8. And the u is 5 plus 8x. Okay. And that is that. Um, well, actually, I'm sorry. We're not done because this is just g prime of x. But now we can just plug everything into the definition of the product rule. Wow, this one is going to be a mess. So f of x is x to the 7th. Then we have this g prime of x, 24, 5 plus 8x squared plus 5 plus 8x cubed. And f prime of x, remember, was simply 7x to the 6th. Oh my God, what a mess. And so you could probably simplify this a little, but I mean that's your answer right there. Um, yeah, you can tell they've been fooling around with it. They've got B there, but it's the same thing. And then they're going to have another one. This one is it's obviously the quotient rule. Yeah, see what they would have had to do here. And then they would have consolidated it. But anyway, so let's go on to the next one. Um, and when this is done, then the next section is, oops, 2.5, which we're not going to have time to do right now. It'll have to wait to the next video, but 2.5, if I remember correctly, is where we introduce another kind of differentiation, which is reserved for special cases. It's called implicit differentiation, and we'll see it's really no different than what we're doing, but it's meant for cases where the expression we have is a mess. Let's just put it that way, where it's not realistically possible to separate out the x and the y variables, and so the rules have to be changed a little. That'll come next time. Right now, we're just going to finish this, and then we'll be done. All right, so I'm going to rewrite it like this because that's the way I like it. Okay. So here's what's going to happen. Think of this as u of x. So we're going to have, okay, so it's the u prime of x that's going to be the challenging part, but luckily, um, it'll be very straightforward because u of x itself is just this ratio. And so this part we can solve with the quotient rule. So think of this as f of x and g of x. And so we're going to have, um, and then we'll just plug them. Now, this implies up here f prime of x would be 1. G prime of x will be 2x. So we'll make the substitutions. X squared plus 7 squared. All right, now we can consolidate this a little bit. Oops, sorry, that's not right. I'm looking at the wrong thing. It's minus 2x squared plus 12x. Now this stays. And then I'll consolidate. You've got negative x squared plus 12x plus 7, all divided by this. Now that's the u prime of x that we needed up here. So now we got some real substitutions to do. So all of this is what we mean by u prime of x. U of x, if you remember, was that ratio x plus 6 over x squared plus 7. Okay, so yeah, we got a mess on our hands here. X plus 6, x squared plus 7, yeah. So, and then we have this piece. And I'm sure they're going to simplify it in the answers here, but that's the answer right there. So, all right. Anyway, so like I said, so we've gone over a little bit here. Um, Next time we'll do 2.5 implicit differentiation. The rules aren't really any different, but unfortunately the notation might be a little different. And also, we have to understand what exactly we're trying to accomplish here and why we need to do this. It only works for a very small number of functions, and which is kind of good news. A lot of people don't appreciate or don't enjoy doing implicit differentiation, but once you get the hang of it, it's just like all the others. It's not that bad. And then there's in 2.6. What is in 2.6? Oh, applications. We're just going to briefly touch on some of these volume problems. We don't want to spend too much time with this. Okay. They just want to remind you what these derivatives can be used for. Like, for example, you can measure the speed with which a cone is filling and things like that. We'll run through this quickly enough, and then we're ready for three. Okay. So, by the way, I did mention this in the last session that if you look in the bright space, you'll see that within each chapter, starting in two, there's a set of problem sets to get us even more practice. And we'll be going over those when we're done with chapter two. So um, the next couple sessions will be quite intense to say the least. All right. So we'll stop right here. And then next time we'll pick it up with 2.5, which is implicit differentiation. Okay. So I'll see you then.